Hello and welcome to the 8th video of the MECH 220 video series. Today we'll be covering conservation of angular momentum. So last time we did conservation of linear momentum, and so this time it's angular momentum. So let's get started with the problem. A 4-pound ball B is traveling around in a circle of radius r1 equals 3 feet with the speed vv1 equals 6 feet per second. If the attached cord is pulled down through the hole with a constant speed of 2 feet per second, determine the ball's speed at the instant r equals 2 feet. How much work has to be done to pull down the cord? Neglect friction and the size of the ball. Alright, so here I'm going to start by using the conservation of angular momentum. And how do I know that I could use conservation of angular momentum versus, let's say, the principle? It's because there's no external torques being put on the system, right? So if there was an external torque, I know that angular momentum would not be conserved. But here, since I'm just pulling the cord down with a constant speed, there's no torque being applied, I can use the conservation of angular momentum. And so in the vector form, we don't need to use the vector form here. Here we can just use the scalar form, which is just mvr. And I'll be more specific here. It's vb1 r1 is equal to mvb2 r2. And that's just saying that the velocity we'll be using here is the tangential or the v theta, right? So the masses can cancel out, so we're left with VB2 is equal to VB1 R1 over R2. VB1 we know is 6 feet per second, R1 is 3 feet, and R2 is 2 feet, which gives us VB2 is equal to 9 feet per second. Alright, and VB2, like I said, it's the same thing as V theta 2, right? Because since we want the speed at the instant r2 equals 2 feet, we want v2, which is going to be the square root of vb2 square plus vr square, right? And why can I use vr? Because I know vr is constant through every point here, right? vr is the same as I'm pulling down the cord. So if this is vr, my vb2 is going this way. So that means my v2 will be somewhere like there. Alright, so I have square root of 9 square plus 2 square, and that gives me 9.22 feet per second. We're halfway done the question, right? And that's the first part. And now the second part is to get the work that has to be done to pull down the cord. And so I see that I have the velocities here, so I can get the kinetic energy somehow, but I don't know anything else. So, but to get the work, I can use the principle of work and energy, right? And I could just isolate for the U1 to 2, and that's my work. So I'm looking for this basically, right? So I can get T1 is half M, which is 4 over 32.2. Remember, this is 4 pounds, so I'm going to convert it into slugs. 4 over 32.2 times, so now my velocity here, do I use VB1 or V1? So let's look at the question more carefully, that the ball is traveling around in a circle with the speed of 6 feet per second, right? So I know it's a little bit tricky, but the question I would interpret, it's very subtle, but the question hints that as soon as you start, you're starting with just the tangential, like VB1 velocity, and later the VR is being applied. So here I'm going to use VB2, and maybe I'll write it down. A VB1 mistake, and that is 6 feet plus U1 to 2 is equal to half, again half m, and now here, which velocity am I going to use? They want the work done, right? And at that instant, at the second instant, I'm gonna have to use the full velocity, my v2, right? The absolute velocity. I'll make a note here. And that is what we just calculated, 9.22 feet per second. So isolating for the work done, we get 3.04 foot-pounds or joules, same thing. But that's our final answer. And we're done the question.